All right, folks. So there was a request for me to go through a separation of variables problem, sort of in video form. So you have all the solutions for these questions on Canvas, but I'll sort of talk through my thought process specifically for. So this is the second example from the separation of variables worksheet. Okay, so let's just start. So we need to solve this PDE. So the only difference between what we did in class and this question is I have Neumann boundary conditions, right? So you'll see I have Neumann rather than Dirichlet. So, okay, let's see what happens. So we start as usual with separation of variables ansatz. So we assume our function u or solution has the form f of x times g of t. So then plugging into the PDE, I have f times g prime. That's the left-hand side because the time derivative equals 3 times f double prime g. And again, that's two space derivatives, so only f gets hit. And rearranging, I'll get 1 over 3 g prime over g, right? Separating all the time stuff on one side equals f double prime of x over f of x. All the space stuff on the other side. So as before, as usual, because these are equal for all space and time, this must be a constant, right? So both expressions must be constant. And as usual, we'll denote this constant by minus lambda. Okay, so first, let me solve the g equation. So on the one hand, I have 1/3 g prime over g equals minus lambda, which becomes g prime equals minus 3 lambda g. So the general solution here is g of t equals e to the minus 3 lambda t. I guess I could throw a constant in front. We know that sort of, it doesn't matter. At the end of the day, I'm going to take linear combinations of everything. So the arbitrary constants you can be a little bit loose with here. It doesn't actually change your final answer. Okay. Now let's go to the, so that was the g equation. Let's now go to my f equation. So I'm going to have f double prime equals minus lambda f, which rearranging gives me f double prime plus lambda f equals 0. Okay, so as usual, we have sort of three cases to solve here, right? So I mean, the characteristic equation that we would get is r squared plus lambda equals 0, from which we know the roots are plus or minus root minus lambda. So, as the previous cases, we have sort of three things to consider. So case one, let me say there's three cases. So case one, if lambda is positive, this is when I have imaginary roots. And so in this case, like we did this in class already, so the general solution should be sines and cosines, right? So C1 sine of root, so let's see, so I want root lambda x plus C2 cosine of root lambda x. Okay, case two would be when lambda equals 0, is when I have a repeated root. In this case, again, as we did in class, I should get C1x plus C2, get a linear function here. And third, case three, when lambda is negative, I'm going to have root of a minus lambda, so now I have real roots. And in this case, we've said, well, it's good to learn how to use the sinh and cosh functions, so I'll go ahead and do that. C2 cosh. Okay. So these are the same cases we saw previously with the Dirichlet problem. Nothing has changed because the ODE, right, f double prime plus lambda f equals 0 hasn't changed. So of course the general solution should be the same. Okay. So now, as usual, I need to start eliminating some of these cases. So in order to figure out which of these I should keep, which I should get rid of, I need to consider now the boundary conditions. So let's consider the boundary conditions. So I was given, right, that ux of 0t equals 0 and that ux of 1t equals 0. So taking this and plugging in my ansatz, right? So u is f times g, so ux, an x derivative would mean f prime times g. So in the first case, I'm plugging in x equals 0 and t is arbitrary. In the second case, again, f prime, because I have an x derivative, plugging in x equals 1 and t is arbitrary. And as usual, because I want non-trivial solutions, I should assume that g is non-zero, right? If g is 0, then everything just zeroes out. So we assume g of t is non-zero. And so that gives us our boundary conditions for f. So f prime of 0 is 0. F prime of 1 is 0. Okay, and so these are the conditions I'll use to check which of these sort of candidate 3 cases should keep and which ones I should get rid of. Okay, so I'll highlight this to remember this is important. And I have sort of these 3 cases to check through, see which of these survive. Okay, so let's go ahead, just do the first case. So when lambda is positive and I have f of x equals c1 sine of root lambda x plus c2 cosine of root lambda x. Well, in this case, I need to plug in the boundary conditions, which means I need to take a derivative, right? I need to check what happens at f prime. So taking a derivative, I'm going to get c1 root lambda cosine of root lambda x. There's a chain rule here, careful. Minus c2 root lambda sine of root lambda x. Again, being careful of the chain rule, so derivative cosine was negative sine, and then chain rule to bring out the extra root lambda. Okay, let's plug in our boundary conditions. So first, when I get f prime of 0, I should get a 0. But plugging it into my expression above, I have c1 root lambda cosine of 0 minus c2 root lambda sine of 0. So this is just 0. This is a 1. So what I'm left with is c1 root lambda. Now I know lambda is not 0 in this case, right? I know in this case lambda is positive. So I know that this is non-zero, which means the only way this equation is true is if c1 equals 0. So the only way this equation holds is if c1 equals 0. Cool. So that tells me that my f of x, right, which used to be some sum of sine and cosine, if c1 is 0, it must only be c2 cosine of root lambda x. But let's plug in our second boundary condition to see what happens there. So f prime of 1 also should be 0. So that's c2. Oh, I dropped. Oh, right. No, so that's fine. So I wrote down f of x, but of course I'm plugging into the f prime function, right? So plugging into the f prime function, the x equals 1. So I already know c1 is 0, so I'm just looking at the rest of it. So minus c2 root lambda sine of root lambda times, and now x is 1. Okay. So again, I'll just simplify a little bit. So minus c2 root lambda sine of root lambda. Okay, so if I'm looking for non-trivial solutions, I don't want c2 to be 0. Root lambda is never 0. So we can ask, is the sine function ever 0? The answer is yes. So this has non-trivial solutions. if sine of root lambda equals 0, which is the same thing as saying, well, root lambda must be a multiple of pi, an integer multiple of pi. So this is some m pi, where m is any integer. Or in other words, lambda should be m squared pi squared. Okay. So, okay, good. So this is a non-trivial solution. So in this case, we do get some candidates for a solution. So f of x is anything of the form. So you can leave the constant in front, you don't have to, but it's cosine of root lambda. So that's m pi x, right? Plugging in my expression for root lambda. And it's sometimes nice to sort of right away just go ahead and write down next to it the associated g function, right? So g is always the same thing way back up here. We know g is always of the form something times e to the minus 3 lambda t. So I'll use that here. So g of t should be something times e to the minus 3 lambda. So that's m squared pi squared t. Okay, so this is combining f and g is going to give us some family of solutions for different m's. Great. Okay, so let me highlight this just so I remember not to forget these later. So this is one family of solutions. Let's check the second case. So when lambda equals 0 case, I had f of x equals c1x plus c2. And again, I'm plugging in my boundary conditions, so I should calculate the derivative. F prime is just c1, right? Let me make sure I wrote it this way before, c1x plus c2, yeah. Okay. So, okay, so I need to plug in. So f prime of 0 should be 0. But when I plug in 0 to the derivative, I just get c1, therefore c1 is 0. So what I've learned from this is that my function f must have the form c2. Now what's interesting though, right, is when I take a derivative of this, right, f prime, it just automatically is 0. And so when I go to check the second boundary condition, f prime of 1 should also be 0. Well, that's true, right? I mean, it automatically was 0 already. So the second boundary condition actually doesn't tell me anything new. So what I've learned from all of this is that f of x equaling just c2, an arbitrary constant, is a solution. So this actually is another non-trivial solution to my equation. Okay, so that's interesting. So again, maybe for completeness, I should write down my associated g. So again, that's something times e to the minus 3 lambda t. But in this case, remember, lambda is 0. So I can simplify this. This is c times e to the 0, or that's just another constant. So this is an interesting case. In this case, so there's g and f. I have f as a constant, g as a constant. So when I multiply those together, I'm just going to get a constant number. Okay, but apparently that's also a solution. And finally, let's check that last case when lambda was negative. That's when I'm going to start getting the sinh and cosh. So c1 sinh of root minus lambda x plus c2 cosh of root minus lambda x. All right, so now you might have to remember some facts about sinh and cosh. They basically behave as derivatives like sine and cosine, but no minus signs pop up. So when I take the derivative of the sinh, it should be c1 root minus lambda cosh of root minus lambda x plus c2 root minus lambda sinh of root minus lambda x. Okay, again, sinh and cosh, the only difference here, right, is that derivative of cosh is not minus sinh, it's just regular plus sinh. Okay. And we continue as before. So now I'm going to plug in 0 to get my first boundary condition satisfied. So that's c1 root minus lambda cosh of 0 plus c2 root minus lambda sinh of 0. Again, this is just 0. This is 1. And so this simplifies to c1 root minus lambda. Just like a previous case, we know that the root minus lambda is non-zero. which means it must be the case that C1 is 0 for this to hold. Okay, so my function f now has simplified a little bit. It now is made entirely of cosh functions. And let's go ahead and plug in now our second boundary condition to see what we learn. So when I plug in 1 into my derivative, so I'm going to get C2 root minus lambda sinh of root minus lambda times 1. And so this is C2 root minus lambda sinh of root minus lambda. Okay, so now important to remember some facts here. Again, the square root of minus lambda is non-zero. And we remember that the sinh function is never 0 if the input is non-zero. And so the only way this expression holds is if C2 itself is 0. So in fact, all we get here is the trivial solution must be trivial, i.e. just the 0 function. So we omit this case, so we ignore this case. Okay, but that gets us there, right? So in summary, we've gotten 2 different families of solutions. One is the cosine looking solutions, another is the constant looking solutions. And so taking a linear combination of all the previous solutions, that'll give us our general solution. So u of xt equals, and so there's a couple ways you can write this. I'll sort of separate the cases out. So on the one hand, I have, the constant fg. So I'll call that, it's a constant. So the convention is often to call that, a0. Okay, some arbitrary constant plus, and now let me add together all the cosine terms. Now, because all of these have the same form, I can put these under an infinite sum, right? Summing over m. So this is going to be a sum from m equals 1 to infinity of, am, again, arbitrary constants in front. Now I'm putting together cosine m pi x e to the minus 3 m squared pi squared t. And yeah, that should do it. That should be my general solution for the Neumann problem. Some people in class noticed, by the way, so you can rewrite this. So I will say what I just wrote is the more typical solution, but sort of remembering properties of cosine and the e function, you could just write this as the sum from 0 to infinity, right? Because when m equals 0, everything just becomes a constant again. So yeah, you're welcome to write it this way if you'd like. Also okay. I will say that the first one is sort of more typical because what we like to do is separate that constant because that doesn't change in time. And then everything else, as you think about time evolving, that's all decaying. So the infinite sum as t goes to infinity goes away, but the constant remains. And so you can actually think about why that makes sense when we talk about Neumann problems. Okay. So yeah, that should do it. So hopefully that's the same answer I got on the worksheet. I don't have it in front of me, so if I got a different answer, it's curious. But I think I think they were the same. So okay, if you have any questions, please let me know. Hopefully this was helpful. All right.